Good morning, everyone. I hope you enjoyed the weekend. We had certainly had some nice weather. So, let's see, a couple of announcements today. One is during the entire term, we've had homework due kind of every Friday. Now we've just started talking about magnetism, and so we're not ready to complete the homework on the magnetism. So the next homework is due on March 29th, which is not this Friday, but the Friday after. So no homework due this week, okay? And then you're gonna do lab number 7. I hope to spend part of today's class getting you ready, talking about what you're gonna do in lab number 7. Make sure you try the pre-lab before your lab section. And then last, the next class on Wednesday will be the Prairie Learn quiz. So quiz number 2, there's a practice quiz on Prairie Learn. The format of the actual quiz will be the same format as the practice. So 10 multiple choice questions. You'll have 40 minutes once you start it. You don't have to be here to write the quiz, but if you want to be here, you can. That's fine. Just bring a device that will allow you to do the quiz. Okay, so the things that we were talking about was sources of magnetic fields, and we discovered that moving charges or currents are a source of magnetic field. And so here's a picture where we had the point charge Q moving horizontally with velocity V, and we said that the magnitude of the magnetic field that it creates at point P will be given by this expression. So mu naught over 4 pi is just some constant. And then it depended on the charge, how fast it was moving, the sign of the angle that the vector r makes from Q to the point P. So the angle theta is between the velocity and that vector r, and then r squared, the distance from the point charge to point P. So it's 1 over r squared. We also worked out the direction of that magnetic field, and we developed a right-hand rule for determining the direction. So I put some figures in here better than I can draw. The right-hand rule for finding the direction of the magnetic field due to a moving charge or a current is to place your thumb of the right hand in the direction of the current, and then your fingers curl around in the direction of the magnetic field. So the magnetic field will always loop around currents. Whether they are looping in a clockwise or counterclockwise sense would depend on the right-hand rule. Okay, good. And then we started talking about this cross product between two vectors. So the cross product of A and B produces another vector C. The magnitude of that vector is just given by AB sine theta, where B sine theta could be expressed as the component of vector B that is perpendicular to vector A. Okay, so in this way, it's had some similarities to dot products. Dot product, the result is AB cos theta. For the cross product, the magnitude is AB sine theta. We had another right-hand rule for determining the direction of the vector C. This one was a little more complicated. There's a few more steps. So what you can do is you take your right hand. Let's do A cross B. So we go in the direction of A, we put our right hand, and then we curl our fingers to be parallel to B. And so B is kind of pointing out of the screen, and then my thumb points up. That's the direction of C. The result of a cross product, A cross B, C will always be perpendicular to both A and B. And so that means it's either pointing up or down with respect to the plane that's formed by A and B. And so whether it's up or down is determined by this right-hand rule. Okay, so what I want to do is I want to go back to our expression for the magnitude of the magnetic field created by a moving point charge And I want to re-express it in a way that we can include the direction information. And so, as you could probably guess, we're going to incorporate the cross product for completing this task. Okay, so we return to the moving point charge, creating the magnetic field at point P. I mean, it's creating magnetic fields all around itself, but we're going to focus in on what the field at P is. Okay, so we'll just draw that picture again. So here's my horizontal dashed line. We'll assume that our point charge is traveling along that line. So here's Q, we'll make it a positive point charge. Here's our velocity V. And we'll go out to some position. This is our position vector R. And here sits point P. And we have our angle theta is right here. All right. So the first thing I'm going to do is I'm going to define a unit vector that's in the direction of our position vector R. And so we'll call this R hat. So R hat is a unit vector. So what unit vector means, of course, is that the length of R hat is just equal to 1. And it is in the direction of R. Okay, so specifically, we could write that the position vector is some length R, whatever the length of that blue vector is, times R hat, where R hat is specifying the direction. Okay, so what I want to do is I want to consider the cross product. We're going to consider V cross R hat. So these are two vectors, and so we could evaluate the cross product. Let's start with the magnitude. So the magnitude of V cross R hat is, well, okay, so what we have to do is we have to take the length of the two vectors and multiply them together, and then multiply that by sine of theta. Okay, so the length of the velocity vector is just the speed. And the length of our unit vector, well, all unit vectors have a length of 1. And so this cross product just evaluates to V sine theta. Now that's pretty interesting, because if we go back and look at our expression for the magnetic field due to this moving charge, that product V times sine theta is exactly in that expression. So if we go back here, we just note that B was equal to mu naught over 4 pi. And then what was it? It was V sine theta over R squared, and then there was a factor of Q there. So the magnitude of this cross product gives us part of our expression for the magnetic field due to the moving charge. The other thing we should do is we should check the direction of this cross product. Okay, so let's just do the direction with our right-hand rule, and then we'll write down the results. So V cross R hat. What we have to do to find the direction is we put our right arm in the direction of the first vector in the cross product. That's the velocity. And so the velocity is just horizontal, so I just put my right arm horizontally. And then I'm going to curl my fingers so that they're parallel to the second vector in the cross product. In this case, it's R hat. And so R hat is just pointing slightly up, so I curl my fingers slightly up. And my thumb gives the direction of that cross product. And so it's out of the screen. Okay, so the direction of V cross R hat is given by the right-hand rule and is out of the screen for the picture that we drew above. There's a convention for specifying directions into or out of a screen or page. And so what we would do for out of the page is we would put a little circle with a dot in it. And so B is out of the page. This little circle with a dot is meant to represent an arrow. So if someone was to shoot an arrow at you, what you would see coming towards you or coming out of the screen would be the tip of the arrow flying towards your face. Okay, so this is the tip of an arrow. Okay, so the convention here is this represents out of the page, and it's an arrow tip. If someone shot an arrow away from you, or say into the screen, what you would see is the feathers of the arrow flying away from you. And the feathers of an arrow look something like this. Yeah, go ahead. Oh, okay. Thanks. So if you see this little circle with a cross in it, that's supposed to represent the backside of an arrow, the feathers flying away from you. And that's how we'll represent directions as being into or out of the page. All right, let's see. Okay, I think we're back. So this represents a direction into the page. And so this is the back or feathers of an arrow. Okay, so what we've noticed then is that this V cross R hat is equal to V sine theta, and it is out of the page, which is, if you recall from the summary right at the beginning, is the same direction as the magnetic field. So it's the same, whoops, same direction as E. All right, so then what we can do is we can replace the V sine theta in that little red box with V cross R hat, and then it has the right magnitude and it gives the right direction for the magnetic field. So the complete vector equation for the magnetic field due to a moving point charge is. Okay, so it's a full vector equation, so we'll put B with a vector sign. The constants are the same, 4 pi, mu naught over 4 pi. And then we had the charge Q. And so now instead of V sine theta, we'll do V cross R hat. And then we had to divide by R squared. So this gives the magnitude and direction. of V. Okay, good. So the other thing I want to do is we've so far identified that magnetic fields can be created by moving charges or currents. And of course, those two things are related because a current is defined as a flow of charge. So how could we recast this equation, not in terms of like a point charge moving with velocity v, but in terms of a current? So that's the next objective. So let's call this equation 1. And so what we'd like to do is we want to re-express one in terms of a current. So equation 1 is definitely correct. So like if you had point charges flying around like a cyclotron or something like that, they would create magnetic fields given by this expression. But often, if we were manipulating charges, we have them flowing through wires in the form of a current. And so it can be more convenient to express this in terms of currents. Okay. So what we'll do is we'll imagine a wire. And so here's our little wire. And I'm going to consider just a little section of it. So we'll highlight the little section, we'll color it red. And so here's a section of wire. And we'll make this section of wire a certain length. We'll call the length delta L. So it's a small piece of the wire, and there's some current I that's flowing through this wire. Okay, fair enough. So the current can be expressed as, well, we know that I is how much charge crosses a surface in a time delta t. So imagine we put an imaginary surface that passes through our wire. We count how much charge crosses that surface in a time delta t. The ratio of that charge and delta t gives the value of the current. Okay, so we're going to do a little bit of trick here. We're going to multiply by 1. But we're going to write our 1 in kind of a special way. And the way we're going to express 1 is we're going to express it as delta L divided by delta L. It's a bit of a silly thing to do, but let's just go with it and see what happens. Okay, so I is going to be delta Q divided by delta T. And then we multiply by delta L over delta L. All right, all I'm going to do is I'm just going to rearrange some of the factors. It doesn't matter which order I write them in. So I'm going to write it like this. I'm going to put delta Q times delta L. So that I didn't change, but I'll swap the order in the denominator. So we'll put delta Q over delta L and then delta L over delta T. So if I had a charge here, Q, we'll call it delta Q, I guess, and it's moving with some velocity v, what does this delta L over delta T represent? Yeah, it represents how fast our charge is moving in our current. And so this is just how far our charge delta Q moves in a time delta T, and that's just its speed. That's exactly what it is. Okay, so therefore we have I is equal to delta Q times V divided by delta L. And all I'm going to do is I'm going to solve for this delta Q V so that, oh, yeah, I need to add a page here. Let's add a page. Okay. So delta Q times V is equal to, what, we just have to multiply by delta T, right? So that's, oh, sorry, I've made a mistake. What mistake have I made? This is not delta T, what is it? Delta L, okay, that's right. So this should be I delta L. All right. Now, why is that useful? Well, if we go back to equation 1, we have a Q times velocity, and now we have a new expression for our charge. We wrote it as delta Q, but it's still our charge times, not velocity, but speed. So that's pretty close to what we had in this equation 1. And if we were able to make a substitution, something like this, then we could re-express that magnetic field in equation 1 in terms of a current rather than a point charge. So to make this a vector equation, we assign a direction to delta L. And the direction that we're going to assign is just, the velocity is obviously the direction that the charge is moving. And so that's the same direction as the current flow. And so we're going to assign the delta L to have a direction in the same direction as the current. So we define delta L such that its direction is parallel to the current I. And if we do that, we could say delta Q times V, where V is now the full velocity, is equal to I times delta L. And we're going to sub this into equation 1. Okay, so let me just rewrite equation 1. Because there's nothing wrong with equation 1. It said the magnetic field was mu naught over 4 pi Q times V cross R hat over R squared. Okay, and so the QV is going to become this I delta L, and that will be our equation 2 after we make the substitution. So therefore, B is equal to mu naught over 4 pi. Let's see, it's going to be I delta L cross R hat R squared. And this is going to be, say, our equation 2. This equation 2 has a name. It's called the Biot-Savart Law, and it gives the magnetic field at point P due to a current segment of length delta L. And so let's just draw a picture of that. So in general, I could have a wire that has whatever shape you like. It doesn't have to be a straight wire, something like this, okay? And so maybe there's a current in this wire of I, and then we highlight one little section. And so we'll say that this is our section here, and this is a length delta L. And then we come out here to some point. Here's point P. This is the position vector R. R hat is a vector of length 1 that's in the direction of R. And we can now write our delta L vector. The delta L vector is going to have the same length as delta L, and its direction will be in the direction of the current. So it's just along the wire. Yep. Sorry, I can't hear you. Oh, so yeah, it's just because we were writing the current as delta Q over delta T. So maybe what I should have done is I should have wrote delta Q from the beginning at the same point, but it's just a little piece of charge. That's all it represents. But yeah, that's a fair question. Okay, good. Now, this expression for equation 2 works only for the red segment, right? It's only works for the little current segment of length delta L. In general, if I want to find the total magnetic field due to this entire current, what I'd have to do is I'd have to add up all the contributions from all the different little current segments along the length of the wire. So I need one more page here. Let's add a page. Okay, so equation 2 gives the magnetic field due to just the red colored segments of the wire to find the net magnetic field due to the entire current in the wire. We have to add up the contributions from all segments. Okay, and so what we could have is we could have next to the red segment, we have a green one. And when we do the green one, the position vector R to point P is a little bit different, and the direction of the velocity is a little bit different. So you have to do that calculation separately. And then we do another segment for this purple one, and we do another one for this blue segment, and so on. And we keep having all these different segments, each contributing a different value of the magnetic field at point P. And to get the total, you would have to add them all up. Now, in general, that's a hard calculation to do. We will try one of them on probably Friday. But ultimately, what we'll do is, because this is so hard to apply, we're going to try to come up with a new method for finding magnetic fields due to currents. That will be called Ampere's law, and that's something we'll probably get to next week. Okay, so with that, I want to do a little bit of an aside, and this aside is going to be to preview lab number 7. So lab number 7. Okay, so what I want to do is I want to consider a loop of current. So let's imagine that we take a wire, we bend it into a circular loop, and we get a current running in that loop. I don't care how the current gets there. Maybe there's a little battery between the two ends. So what we'll have is this loop of wire. Let me draw it kind of big. So here's our, whoops, move that a little bit. Here's our loop of wire. And let's imagine that we have current looping around in this direction. In fact, yeah, okay. All right. Now, what I want to do is I want to figure out the magnetic field that's caused by this loop. And so what did we say? We said, well, we put our thumb in the direction of the current, and our fingers curl around in the direction of the magnetic field. Okay, so let's start on the right-hand side. On the right-hand side, the current's going up. And so I put my finger up, and I have magnetic fields coming out of the screen inside the loop, like to the left of my thumb. And then if I curl it around, my thumb's still up in the direction of the current. On the right-hand side, my fingers go into the screen. And so we must have a magnetic field, in this case, that loops around like so. So it would be coming out of the screen towards us, inside the loop, and it would be going into the screen away from us on the right-hand side of the loop. Okay, we can do the same thing on the left side where the current is going down. This time, when I do the right-hand rule, my thumb points down. To the left, my fingers go into the screen, and to the right, my fingers come out of the screen. Okay, and so we must have over here a magnetic field that also loops around. This time, let's see, it's coming again out of the screen, inside the loop, and it's going into the screen, outside of the loop. Okay, let's just keep going. We have on the top, the current would be going to the left. And so, okay, I put my thumb to the left, and we get another magnetic field that's looping around. It always seems to be coming out of the screen when we go inside the loop, and it's going into the screen when we're outside the loop. Okay, the last thing we have, maybe on the bottom, put my thumb in the direction horizontally, that way my fingers come out of the screen above that current. And so we have this picture here where we have all these little loops where the current or the magnetic field always out of the screen, inside the loop, and into the screen, outside of the loop. So what that tells us is that we have all these magnetic field lines coming out from this middle of this loop, and they all add together. And so the magnetic field is quite strong in the center of this loop. And then it's weaker on the outside because, you know, they're not adding together. They just have these individual loops. There's no destructive or there's no superposition of magnetic fields from a bunch of different places. So what we can do is, let's add a page again. So B is always in the same direction inside the loop. And so we get a strong field. All right, so I'm going to try to draw this current loop kind of horizontally. And so let's give the current some direction. And so this is I. All right, so let's see. I'm going to, just to make this drawing a little bit better, I'm going to actually reverse the current direction and go like this. Okay, good. So if we did this, let's imagine the current is going this way, and it's kind of, that's the part of the loop that's closest to us. So we put our thumb in that direction, and the magnetic field would be pointing upwards through that loop. So what we're going to get is a magnetic field that points upwards through the loop, and then has these rings that kind of loop around. I'm drawing a 2D version of this, but there would be a three-dimensional figure of these magnetic field lines. And so you imagine rotating this 180 degrees to get the full picture of that magnetic field. We've seen that kind of pattern before. Do you recognize it? Where did we see that? It was when we first started talking about magnetic fields. Yeah, it's a bar magnet. So current loop creates a magnetic field that looks just like a bar magnet. So if I was to draw our bar magnet, we would have our north pole here and our south pole here. Magnetic field lines come out of the north pole and go into the south pole. And we can even draw those field lines passing through the bar magnet. And so this looks pretty similar to what we've seen before. And so that's our first observation, is that a current loop creates a magnetic field that is similar to that of a bar magnet. Okay. The next thing I want to do is I want to consider putting a bunch of these current loops side by side by side by side. Let's consider placing a collection of current loops side by side. And that's the figure that I wanted to get to. And so there it is. There's our three current loops. There is current loop 1, 2, and 3. The 1 is going to make the magnetic field lines that look red. 2 is going to make the blue ones, and 3 is going to make the green ones. And I've kind of faded out some of these magnetic field lines and then highlighted others. Okay, what I want to do is I want to look at the net magnetic field at point P. So from current loop 1 at point P, we get this magnetic field B1. And then from current loop 2, we get this magnetic field B2 at point P. And then from the third one, we get this one, which is B3. What would happen approximately if you added up all those three magnetic fields at point P as vectors? Yeah. They more or less cancel out, right? The blue one is horizontal and to the left, and it's pretty strong because point P is close to that second current loop. The red one and the green one both point to the opposite direction. The red one points a little bit up, the green one points a little bit down. When you add those together, the vertical components just cancel, and the horizontal components add to the right. But those two horizontal components will add up to approximately cancel with B2. So if we were to say that this is going to be B1 plus B3, it's approximately equal to B2, just in the opposite direction. And so the conclusion is that for this series of current loops, B is approximately 0 outside the loops or the rings. Okay, we've only done that at one particular point, but you could do that at any point and try to add up the contributions from these three. As long as you're outside these loops, they'll approximately cancel. We could look inside, we could look at a point inside here, and so let's pick a point over here. All right, so there's going to be the red contribution. You can kind of see the red lines are sort of going off to the left, but they're spreading out a little bit. Right along the center, the red one would make a contribution something like this. Okay, so this would be a B1. Let's see, the blue one is also kind of horizontal, you can see the faint blue lines pointing to the right here. It will be a bit stronger because we're close to this current loop, and so maybe there's a B2 over here, something like that. And then there is a, sorry, this would be a B2. And then the green one, we're quite far away from the green one, but you can see the faint green lines are also pointing to the right. Some are going a little bit up, some are going a little bit down. Those two components would cancel, and we would get like a B3, a weak contribution over here. The main point is that all those contributions from those three loops all are pointing in the same direction. So inside the loop, inside the loops, the contributions to, whoops, the contributions to B all add up. Okay. Now, in practice, if you were to build something like this, you wouldn't take a bunch of individual loops and place them side by side, maybe connecting a battery to each of them. Instead, what you could do is you could wind a continuous coil of wire. So to mimic this situation, we can wind a coil of wire. And so this is done all the time. So let's imagine, I'm going to draw a cylinder. And so let's imagine we have a cylinder, and we're just going to use it to wrap wire around. So we'll come up behind, and then we'll loop our wire around and around like so. And we'll make n loops of wire, where n is some integer. Maybe n is how many? 1, 2, 3, 4, 5, 6, 7 in this case. Okay, and we'll put a current I that goes up behind our cylinder and then keeps wrapping around. And so then we end up with a current that's doing something like this. This is basically equivalent to putting a bunch of current loops side by side, but it's much easier to make. You just have one long wire and you just wrap it around the cylinder. Okay, so this is similar to a collection of current loops. And by the argument that we made, outside, we expect the magnetic field to be very weak, because we saw when we have a bunch of current loops collected together, the magnetic field was close to 0 outside. But inside, we're going to have a strong magnetic field, and it's going to look something like this. And so I'll draw a few magnetic field lines here. Okay, so this is going to be our magnetic field. What's the direction? Well, we can put our thumb down. All the currents that are in front of the cylinder are pointing down, so we put our thumb down. And then behind our thumb, inside the bore of the cylinder, my fingers curl and point to the right. And so the magnetic field is pointing off to the right in this case. And so we have this magnetic field. This device has a name. It's called a solenoid. So this coil of wire with current I is called a solenoid. And it creates a uniform magnetic field inside its board. Probably in about a week or so, maybe a little more, we will see that the magnetic field inside, let's just say the magnitude of the magnetic field inside is going to be mu naught N divided by L times I, where our solenoid is going to have a length L. So let's see if I can draw that. This L is the length of the solenoid, and N is the number of turns of wire, the number of loops. So N is the number of loops, and L is the length of the solenoid. And these are used all of the time. So it's not just a kind of theoretical curiosity. If you want to make a uniform magnetic field, the easiest thing to do is just wind a coil of wire and put a current through the wire. Okay, so what you're going to do in lab number 7 is the following. So lab 7 is you're going to have a solenoid to make a uniform magnetic field. So we use a solenoid to make a uniform magnetic field. And so that magnetic field will be, we'll call it BS for solenoid. And it's going to have a strength of mu naught N L times I. You can control the strength of that magnetic field just by varying the current. If you want a stronger magnetic field, you increase the current. Okay. And then we're going to place a compass in the center. And we're going to align the apparatus such that the compass points north and is perpendicular to the solenoid axis. Okay, so let me draw that picture. So we're going to have our solenoid, and so I'll draw my cylinder. And let me draw the compass. I'll put the compass in there first. So here's our compass. Initially, the compass will point north. And so here's north, and here's the compass needle on a rotation axis. And I'll wind my solenoid around here. So here we go. We wind our solenoid. Oh, so here, like that. Okay, so we'll have the Earth's magnetic field. So I'll draw this. Here's the Earth's magnetic field. So we've arranged it so that our solenoid is perpendicular to Earth's magnetic field. If I set the current equal to 0, then the compass just points along the Earth's magnetic field towards the north. Okay? Then what we're going to do is we're going to turn the current on. So I'm going to copy this thing. Oh, why didn't that work? Let's try again. Copy. Paste. All right, good. So here's the Earth's field. All right, so now we make the current not equal to 0. So we have a current coming along like this. And what's going to happen now is we're going to create a magnetic field in the center of the solenoid. So now at the position of the compass, there's a magnetic field due to the Earth. which in our picture is drawn vertically, and a solenoid that is pointing to the left, or sorry, to the right in our case. So the net field at the compass, now the net magnetic field at the compass, I'll be just one more minute, is the Earth, and we're going to add to that the solenoid, and the net result is the net. And that's going to cause your compass needle to rotate. And by how much it rotates is going to be used to determine the strength of the magnetic field. So the compass rotates to align with the net. We're going to use the rotation to measure the Earth. Okay, so the idea is we know the strength of the solenoid magnetic field, and we know how much the compass is rotated, and we can use that information to find the strength of Earth's magnetic field. And so that's what you're going to do. You're going to measure Earth's magnetic field in lab number 7 using very simple equipment, just a coil of wire and a power supply to provide a current. All right, good. Thank you very much, and we'll see you on, well, we'll see you on Friday. Wednesday is the quiz.